Okie dokie then. Welcome to this afternoon video on the joy of covalent bonding. Excuse me. So we're going to look at some basics of covalent bonding today. It's probably only going to be 15 minutes or so. And we will make a start now. So I'm just there. Oh, that's better. So looking at covalent bonding, one of the things, there we go, that is important when we look at any form of bonding is to remember certain things about the periodic table. So you can see up on screen I have a copy of the periodic table. This is an exact copy of the one that you would get given if you are taking GCSE Science with AQA. This is the AQA periodic table. This is the one that is given out in exams as your supplementary sheet in the chemistry papers. So a certain amount of information is given to you. It tells you which number your relative atomic mass is, which number your atomic symbol is, name of the element, and what the proton number is, or atomic number. The bit in red over here on the right hand side is not included. Okay, you have to remember where that is. Okay, but basically you have this step over here. Okay, and that step marks the dividing line between your metals and your non-metals. Anything to the left of the line is a metal. Anything to the right of the line is a non-metal. So as you can see, there's a lot more, hang on a minute, there's a lot more non-metals than there are metals. No, other way around, there are a lot more metals than there are non-metals. So the thing with covalent bonding specifically is that it only involves non-metals. Okay, so it only includes the elements on this section, okay, over here, and hydrogen. Okay, hydrogen doesn't really fit any of the periodic trends within a group, so it tends to float around on its own. Sometimes you may see it over above lithium, above group 1. It is not a group 1 metal. Okay, so hydrogen plus all of these are your non-metals. So you can get covalent bonding in a couple of different situations. You can get it occurring in elements, for example, with diatomic molecules such as oxygen, O2, hydrogen, nitrogen, chlorine, any of the halogens in fact, they all form diatomic molecules. It can also occur in non-metallic compounds, such as, in this case, methane, CH4, ammonia, NH3, and substances such as sulfur dioxide. Equally, you don't just get your elemental version, you don't just get small molecules, you get giant structures, things like graphite, diamond, that sort of thing. Basically, as with ionic bonding, covalent bonding is the same in the sense that the aim is to complete the outer shell of electrons. The electrons are arranged within the shells, and until that shell is complete, it is unstable. So the idea is, first shell has a maximum of 2 electrons, second shell has a maximum of 8 electrons, third has a maximum of 8 electrons. The idea is you want to get 8 in those outer, whichever outer shell you're on, or 2 if it's the very middle shell, the first shell, in order to stabilise it. So with covalent bonding, the big thing is you get the electron shells actually overlap. So rather than the electrons jumping from one atom to another to form ions, like with ionic bonding, you actually get the 2 shells actually overlap, and you get an area in the middle where the electrons are free to move, and consequently you effectively complete both shells at the same time. And the really important thing is you have to know how to do this with dot and cross diagrams. You have to know how to show this. And there are a couple of different ways of doing that. So one example we're going to have a look at is chlorine, which, if you look over here, chlorine is over here in group 7. Okay, and if you remember, you've got numbers across the top, your group numbers. They tell you how many electrons in the outer shell of the atom. So chlorine's in group 7, therefore it has 7 electrons. So you can illustrate this. You don't need to draw all the shells for covalent bonding and dot and cross diagrams, just the outer shell is absolutely fine. You put the element in the middle and pairs, so 2, 4, 6 and 1 on its own is 7. Now what you want is you want to get that to 8. So what can happen is if you overlap, and I'll bring this up on here, if you overlap the electron shells, you can see I've got them here, the electrons from each atom marked differently, one with dots, one with crosses, well they're called dot and cross diagrams. That is how you can tell which electron came from which atom in the first place. So the lone electron from this one moves into this area, this delocalized area, and the lone electron from this one into this area as well. And you end up with 2 shared electrons, and that creates your covalent bond there. So now if you count, you've got your 7 green crosses plus the orange dot, which gives you 8, and 7 orange dots over here, plus your green cross gives you 8. So you now have 2 atoms with a full shell of electrons each. Okay. The result of that type of bonding is that covalent bonding is actually incredibly strong. The small molecules that you might get, like chlorine, have very weak intermolecular forces between them. They are very easy to separate the individual molecules away from each other. But the actual bond itself between the atoms is incredibly strong, which is why when you look at something like diamond is pure covalent bonding. It is incredibly strong. When you look at graphite, it's slightly different. We'll have a look at some more dot and cross diagrams and then I'll come on to graphite, because graphite's, the covalent bonds are still very strong in it, but graphite itself isn't as strong as something like diamond, which they're both pure carbon. So we'll come on to that in a minute. So you've got the idea of this setup with the shared electrons. So what I'm now going to do, I'm going to switch over to this and find a border. There it is. So we'll do a couple of examples. And the first one I want to look at is water, okay, which is H2O. For anyone who is not 100% sure on that, that too only applies to the element before it. Okay, so you've got 2 hydrogen atoms and 1 oxygen atom. So if we draw them out, we've got hydrogen. Now hydrogen is on its own, it's only got 1 electron. Okay, so we've got 2 of those, and we have oxygen, which if you look back at the periodic table, you'll see is in group 6. So it has 1, 2, 3, 4, and I am going to separate these ones this time, just to make it easier to illustrate. Okay. And what will then happen is you'll actually end up with these both overlapping with this one. So, if I do oxygen here, and we'll overlap hydrogen, obviously they are smaller. So this is your hydrogen, that one's a hydrogen, oxygen, 1, 2, 3, 4, 5 and 6. and then your 1 from each hydrogen in there, and like that. So you have oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. It's got a full outer shell. Hydrogen, okay, you're only looking for 2 electrons. Because hydrogen only has 1 shell of electrons, the inner shell only needs 2. Okay, so you have 1, 2, and over here 1, 2, and that's your water molecules. Okay, now you can show that in different ways. That's the dot and cross diagram. Another way of showing a covalent bond is with lines. So in this case, what we'd be looking at is hydrogen, line, oxygen, line, hydrogen. Okay, excuse that. Each of these lines represents a covalent bond. Sometimes what you'll see, and we'll come on to this in a minute, is you'll see it with 2 lines. That's a covalent double bond. Again, we'll look at double bonds in a second. So that example is water. Now, there are plenty of others. Okay, so having done water, let's do... What should we do? Let's do methane. Okay, so for any of you that are quite familiar with your hydrocarbons, methane, ANE, it's an alkane, it's only got single bonds. Meth means it only has 1 carbon. And if you remember, carbon only, carbon forms 4 bonds. So the formula for methane is CH4. 1 carbon atom, 4 hydrogens. Okay, so in this case, we're going to do this. And I'm going to lay it out like this just to make it a bit easier. So carbon is in group 4. It has 4 electrons in its outer shell. Hydrogen is in group, well, hydrogen has 1 electron. So what you can do is you've got 4 hydrogens. So you've got 4, you've got 1 here, 1 here, 1 here, and 1 down here. Okay, what will happen? The shells will overlap, and what you'll end up with, just complete that shell. So you end up with the overlap, as you did with water. So you've now got dot and across, dot and across, dot and across, dot and across, which now means each of your hydrogens has 1, 2, 1, 2, 1, 2, and 1, 2. All your hydrogens now have their full outer shell of 2 electrons, and your carbon has now got 1, 2, 3, 4, 5, 6, 7, 8, which gives you your full shell for carbon as well. Now, again, it does make it incredibly strong. The intermolecular forces between methane molecules, again, quite weak. But the covalent bonds within it that hold the hydrogen to the carbon, incredibly strong. So this one drawn out would be carbon, hydrogen, like that. Okay. You can also, when it comes to the dot and cross setup, instead of having to draw all of that out, you can do it without circles. So, if I show you with methane, methane's quite a useful example for this. So what you do is you put hydrogen with a little circle, and you'd have another hydrogen with a little circle. You have 4 of those. and you've got carbon, and you put the crosses round it. That then goes to carbon, and you just put the dots in. You write the hydrogens. Like that. Okay, it's an alternative way of showing it rather than having to draw the circles out the whole time. One really important piece of information that you have to remember is that, and if I just quickly flick back to a periodic table over here, what you will notice is that some of the symbols are single capital letter, some of them are a capital and a lowercase. It's so important that you make sure you copy your symbol correctly. For example, the ones I usually use as an example of this, carbon is capital C, oxygen is a capital O. Okay, so I'm just going to rub this off quickly. Right. Okay, so carbon is a capital C, oxygen is a capital O. If you look over here, you also have capital C with a lowercase o, which is cobalt. So, switching that, there we go. This is carbon, this is oxygen, and that is cobalt. This is carbon monoxide. Okay, they are not the same thing. It's really important. If you're copying off a periodic table, if it has a capital and a little letter, put a capital and then a lowercase letter. Don't write it all as capitals. Don't write it all lowercase. Okay, they are universally recognised symbols. Right? Okay. Now, looking at double covalent bonds. Okay, and the best example of this is oxygen. Okay, oxygen has one, actually, I can do the simpler version. Oxygen is in group 6, so 1, 2, 3, 4, 5, and 6. So if we've got another one over here, 1, 2, 3, 4, 5, and 6. Okay, and what you will actually end up with happening is when they join together, you will end up with, actually, let me put those slightly further this way. You end up with your 2 free pairs for each, and then these will all go into the same central area as shared. So a double bond means that 2 pairs of electrons are being shared. So if you were to draw that as an overlap, make it actually clear enough to see. If you overlap it, what you'll have is 1, 2, 3, 4. Like that. So you've now got 2, 4, 6 plus your crosses 8, and 2, 4, 6 plus your dots 8. You now have a full outer shell, but you've had to share 2 pairs of electrons. So if you draw that out, you draw it like that. Okay, so if you see an equal sign, it means a double bond. You can get triple bonds. Nitrogen does it. N2 is a nitrogen triple bond. That shares 3 pairs of electrons in that shared area. Okay. Now, looking at specifically diamond and graphite. Okay, they are two quite key pieces, key substances you need to know about. Now, this is to represent a carbon atom. Okay, just grab some little bonds on that one, on that one. So snap them together. And the way the bonds actually form in a carbon atom is because obviously it's not as easy as a straight circle for an electron shell, it's actually a sphere. The electron pairs will spread themselves out as far as they possibly can from each other. They want to be as spaced out as they can be. The best way to do that is in what we refer to as a tetrahedral arrangement, okay, which looks like a little tripod. Okay, so you've got 1, 2, 3 here, and then one on the top here. Okay, and that is the most spread out space you can get with four pairs. Okay, now in something like diamond, what you have is all carbon atoms, and you end up with what's known as a giant lattice. It's a giant tetrahedral lattice. Giant crystalline structure. So, just gathering up as many of my little molly mods as I can. Thank you very much to my dear husband and children who got these for me for Mother's Day. Very exciting. And basically, what you will end up with a situation is you get like a you get a ring forming, but once you start adding onto these as well, you actually end up with more of a kind of, so get that one. It looks more like a net. It's much more kind of structured. I need to find as many of these little bonds as I can find. You know? I'm going to see how big we can make this. That gets me a good few. So let's see what we can do here. Let's put those ones in. Those ones. So every carbon atom still has its 4 bonds. It's just the way it's overlapping. So if I just detach that one for a minute while I straighten this out. So we've got one there, we've got one there, we've got one there, like that, and then like that. So carbon atom, carbon atom, and another one, carbon and carbon. Okay, so you start to end up with it's starting to all interlink as a big structure. And in the case of diamond, that makes it incredibly strong. Okay. However, if you look at something like graphite, which is also pure carbon, okay, it works in pretty much the same way, but instead of being, one second, instead of being a kind of complex crystal structure, what you get is more like, you get almost like a sheet, okay? And obviously in this case, you assume that all of these are spreading out. So you've got a big sheet like this. All of these have still got one electron that doesn't have pair. So they actually form like a cloud of delocalized electrons between layers. So you'd have a layer, then that, and then another load of atoms on top. And what actually happens is the individual layers are incredibly strong. They're very tough to break. But the intermolecular forces between the layers aren't that strong, which is why graphite is very useful as a lubricant. You can use it if you've got a stuck zip. Rub a pencil up and down the zip and it will help it move better. It also is why pencils work in the way that they do. When you write with a pencil, the layers effectively shear off. Okay, the movement between the layers is very, very easy and very smooth. But as I say, the individual sheets are very, very strong. Okay, so what you actually have is graphite is made up of lots and lots and lots of graphene sheet layers. And graphene is incredibly strong. There's a lot of research going on into what we can actually use graphene for because it is as strong as it is. So that's just a little overview of covalent bonding. As I said earlier, if there is anything you want to know information-wise, feel free to message me on here or email Science Mole, and I can pass on GCSE information packs and things like that. Tomorrow morning is forces, so that's suitable for Key Stage 3 as well as GCSE. And I hope to see you then. Okay, so have a lovely day.